Hi everyone, I'm Nick and I'm going to be presenting our paper. We will begin with motivation. Stochastic planning requires stochastic models of the state transition, observation, and objective functions. However, such models are not always available, and attaining them can be difficult, especially when the dynamics of both the robot and the environment must be accounted for. To overcome this difficulty, end-to-end deep learning-based approaches for combined planning and learning have been proposed and have shown promising results. Many architectures have been proposed. These different architectures often share common components, and some of these components even appear repeatedly within a single network. Such components are akin to primitives in planning, and therefore, we hypothesize that improving the efficiency of such components could substantially improve the capability of neural network-based combined planning and learning. This paper focuses on improving the efficiency of one such component, the forward propagation module. That is, the neural network component that propagates information on the basis of learned stochastic models of the state transition function. A straightforward implementation of the forward propagation module often requires many parameters to be learned. Therefore, to reduce training time and data requirement, existing architectures simplify the models being learned. One commonly used approach is to transform states to abstract states, and learn the transition models with respect to these abstract states rather than the original states. Learning an effective transformation may require a deep network, driving up the total number of parameters required. Other architectures learn a state transition function with respect to the entire state space, but reduce the number of parameters to be learned by exploiting the fact that state transitions are generally local, and by assuming that they depend on actions rather than state-action pairs. This is done via weight sharing in a convolution network, where the transition function for each action is represented as a kernel, whose size is much smaller than the size of the state space. This architecture substantially reduces the number of parameters to be learned, but is more constrained in its function representation. To take the best of both worlds, we propose a forward propagation module called the Locally Connected Interrelated Network, or LCI-Net for short. LCI-Net is a forward propagation module that can be embedded into various neural network architectures that combine planning and model learning. The key feature of LCI-Net is the locally connected layer with indirectly interrelated weights. This new type of layer enables efficient information propagation governed by transition models that are more expressive than possible with standard convolution layers, which in turn improves the overall performance and generalization capability. LCI-Net is suitable for multitask learning in partially observable stochastic environments. To show this capability of LCI-Net, we focus on the problem of learning a near-optimal policy, end-to-end, for acting in a parameterized set of partially observable scenarios W theta, where theta is the set of all possible parameter values. Each parameter theta describes properties of the scenarios such as obstacle geometry and materials, position of static and dynamic obstacles, goal location, and initial belief distribution for a given task and environment. The problems of deciding how to act in the various scenarios in W theta are defined as QMDPs with a common state space S, action space A, and observation space O, but without a priori known transition, action, and observation functions. We assume the neural network for solving the above problem embeds an internal model M theta consisting of a state space, action space, and observation space, which are specified manually, and a transition function, observation function, and reward function, which are represented by subnetworks which are trained end-to-end to maximize policy performance. Note that M theta does not necessarily represent the true underlying model. End-to-end learning enables the learned model to be incorrect but useful, differing from the true model, but producing near-optimal policies when combined with the embedded solver in situations where applying the solver directly to the true model would not yield an optimum policy due to solver limitations, such as when the QMDP heuristic is used to approximate QMDP solutions. LCI-Net is a neural network module that learns and propagates information via the transition function ft. It is made up of two interrelated structures. The first structure represents ft and embeds a representation suitable for robust learning, which enables the results of learning to transfer across different tasks in the task domain and generalize beyond the training set. The transition function is parameterized by the current state S, the action A, and the subsequent state S'. A straightforward modelling of such a function results in a very large transition model for problems beyond trivial size. To reduce this learning complexity without sacrificing robustness, known information about the problem structure should be encoded in the neural network representation of the transition function. Spatial convolution layers have often been used for this purpose, as they encode the constraints of locality and positional invariance. The value of an output is influenced only by inputs within some local neighbourhood of the position of the output, and is independent of the position of the output itself. The locality assumption is desirable for transition functions, as in general only local environment features influence the effective actions within a single time step. However, the positional invariance assumption is problematic. This invariance assumes that the local information is the same in all parts of the state space, which in general is false, failing to capture important characteristics such as the dynamic differences between a mobile robot moving in free space and moving near an obstacle, and between a robotic grasper applying force inside and outside the friction cone of a surface. To relax the restriction on positional invariance while still encoding locality, we formulate a representation of the transition model T, which depends on S, A, and delta S, the relative change to S after action A is performed. The transition probabilities for any state S depend only on the local features of S. Under this formulation, the transition probability is learned for each combination of state-local features, action, and relative change in state. The supported T is constrained in each dimension to lie within the maximum distance the agent can move in one time step. A spatial convolution network is used to learn FT. However, unlike existing approaches in which the learned independent kernel weights represent transition probabilities, LCI-Net learns a set of kernel weights to predict the transition probabilities for each combination of action and relative change in state based on local environment features. These learned weights are shared, enabling information learned about the transition probabilities for one state to generalize to other states. The number of learned weights can be made independent of the size of the state space, allowing a transition model trained on a set of small environments to be applied in larger environments for evaluation, thereby improving scalability and generalization capability. The second structure efficiently propagates information such as state action values and beliefs through space over a single time step, in accordance with the learned transition function. To enable information such as state action values or beliefs to be propagated based on a set of transition probabilities in the form T, S, A, delta S, LCI-Net constructs locally connected layers with indirectly interrelated weights. An overview of this new structure is shown here. The structure operates on a tensor representing some function defined over the state space at some time step T. This tensor may represent information such as a set of state values or a belief distribution. The structure duplicates this input to create one copy for each available action, with these copies stacked along a new axis, with the size of this axis equal to the number of available actions. For each action, the input is then further duplicated to create one copy for each possible relative change in state, delta S, with a shift operation applied corresponding to the relative change. These are stacked along an additional new axis, with size equal to the number of possible relative changes in position. These can be either every possible move within some fixed distance, or maybe a restricted subset, such as north, south, east, and west directions only in two-dimensional space. This gives a tensor which can be indexed by S, A, and delta S, and hence has the same dimensions as a transition model T produced by the subnetwork FT. This tensor is multiplied by T, before being summed along the axis corresponding to delta S, to produce an output representing the expected future value of the input function after transition dynamics are applied. Further details on the motivation and implementation for this structure are available in the paper. This new type of structure provides a compromise which combines the superior generalization capability of spatial convolution layers with the greater expressiveness of locally connected layers, while encoding algorithmic priors that are well suited to the problems of planning and state estimation. A particular strength of this structure is efficiency in terms of the number of parameters. Let R be the maximum range within which the agent can move in one time step, or equivalently, the maximum distance within which an environment feature, such as an obstacle, can influence the movement of an agent. This range corresponds to a convolution kernel width of 2r plus 1, which we denote as k. This kernel width applies to both the transition dynamics convolution in prior methods and the FT network in LCI-Net. In LCI-Net, the number of channels is equal to the product of the size of the action space A, the number of shift directions D, giving a total number of learnable parameters as k squared A D, compared with k squared A parameters for previous methods, where the number of channels is equal to the number of available actions. No additional parameters are introduced outside of the FT component network. When all possible shifts within the maximum range R are considered and the number of state dimensions is fixed, the value of D is independent of the number of states. This gives linear complexity in terms of the number of actions and constant complexity in terms of the number of states, equal to that of prior methods. In terms of the number of operations required, LCI-Net requires one multiplication and one addition for each combination of state, action, shift direction, and kernel position. Additionally, a shift operation is required for each state. This gives a computational complexity proportional to k squared AD plus 1 multiplied by S, where S is the size of the state space. Here, D can be considered constant when the number of spatial dimensions and maximum movement range are below some fixed maximum. As a comparison, prior methods require one multiplication and one addition for each combination of state, action, and kernel position, resulting in a total number of operations proportional to k squared AS. Therefore, LCI-Net and previous methods have identical computational time complexity in terms of state and action space size. In general, the value of D has linear complexity with respect to the transition range R and the number of state space dimensions. However, scalability can be further improved by restricting the set of shifts to a subset of all possible shifts. Our experimental results indicate that certain restrictions do not detrimentally affect policy performance or learner conversion speed. In this work, we demonstrate the potential of LCI-Net by using it to replace the forward propagation module of QMDP-Net. QMDP-Net's overall architecture consists of two components, planning and belief update. The planning component approximates the optimum value function using the QMDP heuristic. QMDP-Net adopted the value iteration implementation of VIN, or value iteration networks, where value iteration is implemented as a recurrent neural network. This network consists of a repeating block structure, in which each block represents a single step of value iteration, and blocks can be stacked to arbitrary depths to produce any desired planning horizon. Each value iteration block contains a forward propagation module that computes the intermediate value, Vt plus 1. We replace this forward propagation module in each value iteration block with LCI-Net, as shown in this diagram. Each value iteration block takes as input a value image VTS and outputs an updated value image based on one additional planning step, VT plus 1S. The input to the first block, V0S, is taken from the prediction of the immediate reward associated with each state, provided by the reward function subnetwork. In this application, LCI-Net takes VTS as input and outputs an intermediate value V prime T plus 1 SA. The reward image RSA is then summed with V prime T plus 1 SA to incorporate the immediate reward received at time step T plus 1, yielding Q T plus 1 SA. V T plus 1 S is then produced by selecting the action channel of Qt plus 1 with the greatest expected return. The belief update component maintains a belief distribution, which is updated at each time step based on Bayesian inference. In QMDP-Net, this is performed by applying a neural network-based histogram filter called ITEE-HF to compute the posterior belief. The forward propagation module is used in this filter to compute the intermediate value B prime, which denotes the belief after the effective transition has been applied and before accounting for the likelihood of the received observation. We replace this module in the belief update block with LCI-Net, as shown in this diagram. This belief update block takes a prior belief BT, an action AT, and an observation OT as input, and produces the updated belief BT+1 as output, which is stored as the prior belief for the next action selection. In this application, LCI-Net is applied to the prior belief image to produce B'T+1 SA, the belief propagated forward by one time step after some action A is performed. This tensor is indexed based on the performed action AT, with the channel corresponding to AT retained and all other channels discarded, giving B'S the updated prior belief. In parallel, the observation model produced by the observation function subnetwork, ZSO, is indexed based on the perceived observation OT, with the channel corresponding to OT selected to give ZS the likelihood of each state based on the perceived observation. BS and ZS are then multiplied and normalized to give the posterior belief Bt+1S. We compare this LCI-Net modified variant of QMDP-Net with the original QMDP-Net on a variety of partially observable stochastic environments. Both networks are trained via imitation learning, using the same set of expert trajectories, with the expert trajectories generated by applying the QMDP heuristic algorithm to manually constructed ground truth POMDP models. Only trajectories where the expert was successful were included in the training set. The networks interact only with the expert trajectories and not with the ground truth model. All hyperparameters for both networks are set to match those used in the QMDP-Net experiments. We tested the networks on 4 domain types. First, a navigation problem in a 2D maze environment with structure that mutates during runtime in a way which qualitatively affects the optimum policy, designed to measure the robustness of a policy to dynamic environments. Next, a navigation problem in large-scale realistic environments, where the networks are trained on small artificial environments of sizes 10 by 10 and 20 by 20, before being evaluated on environments modeled on LiDAR maps from the robotics dataset repository, with size on the order of 100 by 100. Third, an environment simulating a 3D multi-rotor drone navigation problem. And finally, a grasping task in which a robot must localize and grip objects in 2 and 3 dimensions, using only observations provided by touch sensors. Our results demonstrate that LCI-Net, despite representing only a relatively small change in the network architecture of QMDP-Net, is able to deliver significant increases in performance and efficiency. A summary of key results is shown. Replacing only the forward propagation component of QMDP-Net with LCI-Net improves its generalization capability by a factor of up to 10, as well as giving rise to consistent improvements in success rate and collision rate across a wide variety of domains. The more expressive transition operator incorporated in LCI-Net introduces only a small amount of extra complexity. The additional time required per epoch of training is small in most cases, and is often compensated for by a decrease in the number of epochs of training required to reach convergence. In most cases, the additional amount of memory consumed by LCI-Net is negligible relative to total memory consumption. While scaling to larger environments results in an increase in required memory, the rate of growth in memory consumption is very close to that of QMDP-Net. This video demonstrates how the more expressive transition model learned by LCI-Net enables a significantly improved policy to be inferred. Here, 2 agents based on the original QMDP-Net and an LCI-Net variant, respectively, must localize and navigate to a goal position in a dynamic maze environment. With LCI-Net, the agent maintains an accurate belief distribution, even when receiving noisy observations, enabling higher confidence about the outcome of selected actions, which leads to better navigation performance. In summary, LCI-Net is a neural network module that can be used for forward propagation in architectures for deep learning for planning. It efficiently learns an expressive transition model which uses abstract states as input while being applied to original states. It enables significant gains in planning performance and generalization with minimal additional computational complexity. This work suggests that improvements in the structure of small components which have been used repeatedly in end-to-end learning architectures have the potential to create significant gains in performance.